Hi guys, welcome to SCUDEM number 7 2022. Our team number is 1127, and we have chosen problem 8, introducing stress. Team member 1 is Wendy, also from New York University. Team member 2 is James Jane, also from New York University. So first I'll talk about some assumptions that we make in our process. So first, we assume that stress affects all astronauts' productivity in the same way. Number 2, we assume that incoming astronauts has the same capabilities as existing astronauts. So as they have been through the same process of training and stuff, we assume that they will perform similarly in this International Space Station. Third, astronauts' capability depend on stress only and don't improve over time. 4, we assume that astronauts all have the same schedule and work the same amount of time. We assume that they cope with the same schedules, so they will be affected by the rest component, they will be affected by the stress component similarly. 5, once new astronaut arrives, the number of astronauts remain the same. And so now we come into the actual part of deriving our equations. So part 1, I will talk about variables and ODE. So first, variables. We have an abstract stress quantity, which we name it S with respect to time. We have an abstract efficiency, E, also with respect to time. And we have number of people, N. Rest, R. Work done, W, which is all pretty self-explanatory, given by the first letter of the word. And now here's time for basic equations. So we derive the equation of stress with respect to time, which is negative t cubed over 2n plus ct plus r plus k. Over here, n is the number of people, r is the amount of rest, and c and k are the constants. And then the change in stress over change in time will be negative t over n plus e, which is efficiency. Efficiency has the equation of 1 over 3 t cubed minus n over 2t squared plus k. And the changing in efficiency over changing time is t squared minus nt. So how we derive the equations is that when we are considering stress, we put the factor of efficiency into stress. So when we conduct the changing stress over changing t, we put it as negative t over number of people plus how the efficiency of the astronauts expected to do more work, and the stress of the astronauts will accordingly increase. And then we come up with this equation of work done, which is equal to efficiency plus stress. So this is the final equation of work done. On the bottom, 1 is n, 1 is n2. This will represent a constant for this equation based on the number of astronauts in the space station.
Recall that earlier, work is a combination of stress and efficiency of the astronauts. So now let's show how we have obtained that equation. Remember that stress and efficiency affect each other, and for us to isolate either of them, we have to first subtract our derivative of efficiency from the derivative of stress. By moving the derivative of efficiency term to the left-hand side of the stress equation, we can cancel that out and leave us with a right-hand side only filled with expressions in terms of t. Given that this is a linear differential equation, we would like to apply the technique of integration by parts and using the integration factor of e to the t in the process. In this case, the integration by parts would involve both the integral of t times e to the t as well as t squared times e to the t. But luckily, for t squared times e to the t, we could apply our results from t times e to the t and obtain a simpler derivation overall. Also notice that here we yield 3 constants, 1 from the integral of the left-hand side, and 2 from the separate 2 integration by parts from the right-hand side. Simplifying, we factor out all terms containing e to the t, which leaves us with constants that has e to the t in their denominator. We group out these constants onto the right-hand side, and this allows us to get rid of the negatives because of the property of constants, and we can write e to the t as their common denominator. And finally, we obtain an equation for stress solely expressed in terms of t. And this equation would then allow us to produce the work equation that we have shown from before. Now, doing the opposite of what we just did, we're going to add the derivative of e to the derivative of s. This part is going to involve the same sort of manipulated equation for stress, where the e term is on the left-hand side. And by performing this simple addition, we're going to get 2 derivatives on the left-hand side, which we could combine. Now this part requires the assumption that astronauts are going to perform uniformly under the same stress conditions, and they're all going to work towards the tasks that they have been assigned to. However, by applying integration, we're able to solely focus on the right-hand side, which contains most of the non-trivial terms, including t, and the result of s that we have produced from before. Now this involves both the separate integration of each t containing term, as well as pulling our results from s and combining all of these into one single expression. And also note that we have factored out the t squared term to produce a constant expressed in terms of n. The same thing also applies for the t term, which also contains a coefficient that is a constant solely expressed in terms of n.
I will continue to talk about part 3, describing different scenarios with our work equation with respect to time. So this is our final graph. The green line is the work equation, the red line is the stress equation, and we set the rest to 6, the number of new astronauts to 4, and K1, K2, and K3 are just our constants. And so I'll take you guys to this page. So first we can play around with the amount of stress. So as stress decreases, the number of work done decreases, stress increases, just because if we don't have rest, we get overload and our efficiency won't be as good. However, as rest increases, the work done increase and the stress level decreases. But then you can't get to too extreme cases. And then we can look at the number of astronauts. So as the number of astronauts decreases, their stress level overall decreases, their work done overall increases. We also cannot have too much people in the space station. The work done will decrease and the stress level will increase. Variable x equals 7, that is actually what we scale our time. It will be 7 weeks, a little bit around 2 months. That will be the mission time of the astronauts. And that will be the end of. So here's kind of an overview of what we get from playing around with our variables.